My name is Marcin Driański, and I'm the co-founder and consultant at Remedo Labs, a spin-off of the Poznań University of Technology in Poland, focusing on wireless communications, Open RAN, and 5G and beyond. And our session today is on network slicing in oran, where I'd like to touch upon the overall concept of network slicing as we know it from 5G world and from 3GPP specs, and then focus on details how it's treated within oran. So let's get down to the contents. We'll start with a network slicing overview, as mentioned in a second, where we are going to discuss the concept itself and several details regarding the radio access network. And then we'll speak about, for those of you who are not participants of the oran system training, we're going to get into the oran architecture to sketch the overall concept in the oran, and then we'll speak about how those two aspects merge together in section number 3, which is network slicing in oran, so how it's treated by the Oran Alliance. And there will be examples of how it's modeled, what are the important aspects, how the different entities in the oran architecture relate to network slicing. And then we're going to cover 2 use cases. First is RAN slice SLA assurance. So how within oran specifications this is treated, how the different entities relate to that, what are the important aspects to take into account in terms of measurements, and how to force the RAN to behave in such a way that the slice SLA is assured. And then the second use case we're going to cover today is NSSI or slice. We're going to get to those abbreviations. But this is how the slice resource allocation optimization might be taken, and also we're going to touch upon how the different entities in the oran architecture are interacting with each other. And here we are specifically going to take a look at the signaling flow so that we know what's happening around and how to assure those aspects. And then finally, of course, there will be a summary where we are going to summarize all those things that we discussed during the presentation. So let's get down to the actual content, and we'll start with network slicing. Network slicing, what it is and how it fits into the overall picture of mobile networks. So network slicing is basically using a single physical infrastructure that allows to virtualize and provide multiple logical network that those multiple logical networks basically shall fulfill different requirements or are defined for different tenants, like different operators who want to provide the service through, let's say, a 5G network. And regarding that, the network slice, so a portion or an individual logical network sitting on the common infrastructure, comprises a set of network functions supporting the communication services for a particular use case. And that might be referring to different use cases, like we'll see in a second, like V2X or MTC or mobile broadband, but this also could be different services and the same use case but for different operators, or a same use case for the same operator for the different purposes, like the private network versus the public access. So if we take a look at the overall architecture, from the right side we have UE, then we have the base station or RAN, then we have the edge cloud, core cloud, and the services, and here we are mentioning internet access. Now, so below we have the infrastructure where there is a base station, edge cloud, core, regional cloud, and then we put on top of that the functionality in terms of virtual instances. So one of the slice might be, for example, eMBB slice that we want to assure 20 gigabits video for a UE. And then we place, of course, the RF part in the G node B or at the cell site, and that might be remote unit. And then we have an edge cloud that is basically taking all the processing with CU and DU from the oran world, that is taking or connecting to several RF or radio remote units. And then for the video, we might be providing that through a local buffering. So we put a cache functionality in the edge cloud, whereas all the other ones like mobility management, charging, session management, and access management, they are put more centrally to the core cloud. Whereas for another use case, that is more importantly to serve a lot of devices like the MMTC or machine type communications, massive machine type communications, where it's more important to have to, for example, in that case, 200 devices per square kilometer, reporting not too often and also not moving, which means that we, for example, do not have the mobility management function that was there in the previous use case. And we put everything centrally, so we don't have a cache here. We only serve those the radio access close to those UEs, but then all the processing and all the management of that particular network is sitting back in the core cloud to get pooling effects. And then yet another example, that's the V2X slice. In that case, there is yet another different important aspects to cover, where we have as UEs cars, and for those it's important to have 5 millisecond latency. And in that case, if this is the requirement, then we need to put as much functionality as possible close to the edge, so that we can capture this little round trip time as close or as fast as possible. That means we need to put those functionality like session management or mobility management or access management close to the edge and putting that in the edge cloud. Whereas we only leave charging at the core cloud, it's only where the device is just repeating or having the signaling once in a while, and it's not important for that to be close to the edge as well. And then the important part here is to cover the low latency requirements. So all in all, having all those different requirements and different use cases, as we might see, we might put different parts or different functionality, the same functionality, or different versions of that functionality or instance on the different places, depending on where it's needed, depending on the requirements. And this is the whole concept that the network slicing is taking. So we have a single infrastructure, we put the functionality where it's needed, depending on the use case and application. So that's, let's say, the overview. Now, getting down to a little bit more details on that, let's start with the terminology, because we will see how it all fits together, and then how it relates, of course, to the oran. So we have a network slice instance. So that's basically a one set that we saw on the previous slide. That's a set of network functions and resources arranged in a specific way and forming a complete logical network. So this single thing, it's called a network slice, or more particularly, that's a network slice instance. Then network slice subnet instance, NSSI. So that's a sort of a set of network functions arranged to form a logical network. And that might be, of course, with relation to RAN, and then RAN and the core network, that might be two separate network slice subnet instances, whereas both of them create a full network slice instance. We are going to see the details later on. And then there is a network slice subnet template. That's basically a description or a recipe for all the elements that are needed to create a network slice subnet instance, basically explaining what are the different entities that are needed to support a certain use case. Then we have a network slice template, which is a bigger thing. It's again taking from a higher level view the description of the structure to create a network slice. And then finally, we have physical resource isolation. That's basically a regime of resource management where the physical resource used by one network slice instance cannot be shared with another network slice instance. So basically, what it means is we might have a defined or set of physical resource blocks or other resources that are dedicated for a particular network slice instance or a network or basically a network slice. So again, network slice instance, the whole network, let's say virtual network to support certain use case, network slice subnet instance, the different portions of the network to create the whole network instance, getting the resources and elements and functionality that is needed there, and then the templates for those so that we know that's a recipe how we create those instances. And then finally, when we got to the physical resources, they need to be some kind isolated. There is a need so that this is isolated, and we'll see that in the requirements from the 3GPP. So getting those in place, on top of everything, we have a service layer. So we want to have to provide certain service. That's an instance of an end user service or business service that is realized by a network slice like MBB or V2X service or MBB for private networking and things like that. Then below we have the network slice instance layer where we have network slice instances, again, refer to the previous one, that might be composed of several sub-network instances. So we might have one network instance that is composed of the radio access network, core network, and also transport network, and they might be shared between different slices. So that's basically network slice instance. Again, it's a set of network functions and resources to run those to create the complete instantiated logical network. And those could be shared between different network instances. Whereas the subnetwork instance, set of network functions and resources for those, and they might be shared by multiple NSIs. So for example, network slice instance 2 and network slice instance 3 are sharing the same yellow subnetwork instance. For example, that could be radio access network, whereas they have two different subnetwork instances for the core network instantiation. They are of course mapped one to another. So service layer is using certain network slice instance, and then below we have resource layers. That's basically a physical infrastructure, physical set of assets for computation, storage, transport, including the radio access. So including the radio access network, including the CUs, DUs, and RUs. And they are, of course, mapped to, or of course, cloud services as well. They are, of course, mapped, so the subnetwork instances are mapped to the resources, network infrastructure, and network functions. So this is how it all looks in terms of, let's say, an abstract nomenclature and abstract element. Now let's get down to the concrete examples. Where we have the next generation oran that we are going to discuss later with the oran architecture part. But here it is a single black box. But speaking of slices, this is the one that is shared. This is the one where we need, and what is important here, that we need isolation. We need mechanism for isolation. We need mechanism to protect the resources from one slice to another one. Whereas the other ones, for the core network part, they are more flexible because we use, for example, some of those cloud services and where the resources are not that scarce as at the RAN area. So what do we have here? If we have a UE, or a device that might be connected to multiple slices, having, for example, slice B service or slice A service, and those slice services, those services provided by slices, are, let's say, a complete network sets where we have portions that are common for those slices, so common control plane network functions. And then we have individual or separate network functions for control plane, like session management. And then we have a separate user plane function. So core network user plane functions, that's the user plane UPF from the 5G world. That is basically assigning, for example, different IP addresses and having access to different resources or different services. There are of course aspects that are common to everything, like slice selection function. So we need firstly to be connected to a certain slice via this slice selection function. And then, of course, there is a subscriber repository that is pointing to certain subscribers that could subscribe to certain slice. So again, summarizing this, from the core network perspective, there are functions like session management function or user plane function that are dedicated to a slice. What I mean by that is that basically they define how to control a slice, how to create barriers, how to connect to the network. And then there is a common control plane network function, and this, of course, is AMF, so access and mobility function. This is where the UE is connecting independently on what type of slice is it connected to, or does it want to have to be connected. And then connecting to that, it gets the resources from and access to the services from different network slices. From the RAN perspective, not going to read all of those, just pointing several aspects. This is an extract from the 3GPP document defining how network slicing is impacted in the RAN. So what are the important aspects in the RAN and GRAN? And then this is, of course, then reflected in the ORAN. This is where the ORAN takes place. For example, in the case where we need to assure resource isolation, availability of the resources, selection of the resources, and awareness between the different aspects, as well as radio resource management. And this is where we are going to link that part regarding to slicing to the ORAN thing. So the area like RAN awareness of slices, so the NG-RAN need to be supporting different slices, need to support also differentiated handling of the slices for different slices. Like for one, it might be mobility management and handover procedures, whereas there is another one that does not need an handover procedure, like those massive machine type communications. Then there is a need for selection of the RAN part for the network slice. This is need to be supported by the NG-RAN, so 5G-RAN using the assistance information. This is where NSSI, so the serving subnet slice ID is used. Then there is a need, and this is of particular importance in our case, for resource management between slices. So this is directly related to the ORAN thing, meaning that the RAN need to support policy enforcement between slices per SLA. And this is our use case that we are going to discuss later on, to assure the SLA for individual slice. And what happens if something changes, like we need more resources, how to reschedule those resources. Single NG-RAN need to support multiple slices. So it's not that individual, let's say, base stations only support one network slice. They need to support multiple of them, and that should be free to apply best RRM policy for the SLA where the slice is supported. So it's also related to the location of the services that are provided. So there might be a full 5G network, a full NG-RAN, a set of base stations, and only in one location we support those, and there is a need for that functionality. For example, that might be a traffic steering where it works where there is a mobility that's still the same network, and it's only in the place where that mobility takes place for a specific slice, whereas it's not used for another one when there is, for example, a place in a city when only the measurement comes from the machine type communication devices. And other things like support of quality of service within a slice, resource isolation between slices. by means of radio resource management policies and protection mechanisms. This is again where we are going to speak about that within the ORAN discussion. Congestion in one slice should not compromise SLA of another slice. This is again the protection mechanism between slices and the isolation. Of course, that might be a dynamic change of the resource allocation, but the SLA need to be protected there. Again, slice availability related to the part of the network, the location. It might be provided in one part of the city and not in another one. And the UE might be associated to multiple slices. That's why we need the slice ID at the UE communication. It could have at the same time be connected to two different slices, like MBB slice and V2X slice if it's a single car, for example. And now how this life cycle is operated. Again, remember that's using a virtual instances of the network functionality. So we have a first part where we use the recipe. We design a network slice instance template, onboard it, prepare the network, and then start commissioning and creation of the slice, and then activation, reporting, supervision, modification of certain aspects. This is again where the resource management comes into play. And then we might deactivate the slice instance and then the commission and terminate. And this should be sort of a dynamic way. And this is where it's needed to have dynamic and automation within management of the network slice. And this is again why it's needed, or why it's important part of why it's important part in the ORAN area, because this is where the ORAN takes place in terms of the management, the API towards the network management, and then going down to policies and the near real-time rig. Different entities are working on slicing, so different SDOs or standard organization bodies like 3GPP. A lot of that, it's all related to 5G. Then we have ONAP, then we have ETSI, and then we also have GSMA working on different aspects, including use cases, including architectural requirements, including management and orchestration, where the whole life cycle takes place, slice configuration, then security is very important, and then fault management and KPIs, performance management, and optimization of a slice. So that's, you'll get those slides, of course, so then you'll have the references to specific slicing aspects within different SDOs. So that would be, let's say, the end of our introduction to what slicing is. Again, that is a set of functionality creating the whole network, providing the specific service on a different manners for different types of use cases. Okay, so a short review of the ORAN architecture. In general, the ORAN is created by disaggregating the radio access network. So now we are focusing only on the, or maybe not only, but on the NG-RAN, so next generation radio access network, where there are base stations, and those base stations are split into several sub entities like ORU, ORAN remote unit, ODU, distributed unit, CUUP, control, central unit, user plane, and central using control plane. And that whole creates a 5G base station. And then there is a rig defined in ORAN alliance that is a controller operating in a near real-time control loop, getting the information and feedback and performance measurements from the entities regarding the connectivity, regarding the resource utilization, and then providing the commands like, I don't know, handover commands or interference management or resource selection or resource reservation and things like that. And that's in the, let's say, control loop of larger than 10 milliseconds and less than 1 second. And then on top of that, and that's still in the RAN domain, so that could be seen as a part of the base station. It could be also a separate entity, but it's also part of the base station. And then there is a non-real-time rig within the management plane. SMO is service management and orchestration. So that's sort of a MANO management plane where via policies, the near real-time rig is getting those, let's say, boundaries of, for example, what cells AOE could be accessing. In our case, for example, what cells are dedicated for a specific slice, or what are the bandwidth that is required for a specific user in a slice, and things like that. And that's in the order of seconds or more. So that's sort of a management control loop. So those orange ones are defined by Oran Alliance. The blue ones are defined by FreeGPP, with the O including the functionality defined by the Oran that supports that the base station is supporting the Oran capabilities and interfaces. There are several important interfaces here. One is A1, already mentioned. So it's provided via the non-real-time rig. The machine model learning is coming down. Policy enrichment information to the near real-time rig, and policy feedback goes up over O1 to the management plane. Then there are X apps. Those are the actual radio resource management functionality, like traffic steering, interference management, mobility management, load balancing, robustness optimization. So all those RRM and some functionalities are sitting and being accessed via the near real-time rig over APIs. And then the near real-time rig taking those decisions provided by the X apps are being then fed to the actual entities, to the actual base station parts, including, for example, control, monitor, suspend actions. And that might be, for example, providing or getting a user to be switched from one cell to another one, and then going up from the ODUs and OCUs, data collection, feedback to the near real-time rig, and then we have the control of using E2 interface. Then we have the FCAPS protocols for reconfiguration of the resources, discovery, registration, and performance and resource updates. We're going to have a look on how it's working with the reconfiguration part, so how non-real-time rig in terms of slicing configuration goes down to the ODU, how it could reconfigure the resources depending on the needs. And then there is one other for open front haul endpoint to control the remote unit, which is the lower part of the physical layer and the RF part. And then O2 to actually control the O-Cloud. The O-Cloud is basically the cloud computing platform on which we could put all those entities, and that could be controlled and the resources can be steered. And speaking of those, all of them could be in principle virtual machines or Docker containers or service microservices that are running on the virtual instances. They could be scaled in and scaled out, so that depending on what the resource need is. And then due to that, they are perfectly suitable for network slicing, basically because we could have multiple instances. They need to the resources can be scaled in and scaled out, of course, apart from the radio resources. So the bandwidth, the carrier that is allocated to the transmission, in that sense, they need to merge somehow. That's why we need to use the slicing concept, for example, for the partitioning. So summarizing, we split the base station into several subcomponents. For the control part, for the user plane part, for the lower protocol stack part, for the upper protocol stack. Then we extract and abstract out the near real-time rig, and then the management plane. And having those, we need to control that via policies. We can scale in, scale out. We can create new instances of slices and create, and then need to protect and assure SLA. This is going to be provided in the next sections. So now how this oran thing fits into the slicing thing, how they two merge, what are the important aspects in those. So first of all, the oran defines an oran slicing architecture. Basically, this is what we saw just before. We've added special functions to the slicing management aspects. And by the way, on the right-hand side, you have all those explained. Of course, you will get the abbreviation and glossary list later on. But because of having slicing with all those different virtual and functions and things like that, this is really cumbersome to get and memorize all those. The important part is that we have those that we already discussed. So network slice subnet, a part of the network that is then composed into network slice. We have virtualized network functions. Those are the actual network functions like OCU, CPU, CUUP that are provided as a virtual functionality and also in the core network as well. And then we have the management functions for those. So we have network slice management function and network slice subnet management function. So separate functions to manage the overall slice of the network. Now those are placed in the SMO. So this is where the management takes place. This is where we can initiate and then close a slice. We need to have certain resources. Not going to go into the details of those. That would be another session and another 2-hour discussion on those. The important part is that there is a hierarchy here. This is a network slice management function and then a sub slice or a subnet, which is the RAN management function. And then there is an individual network function management function. So this is how it's organized, right? We have slice, then we have sub slice or subnet, and then we have the function in those, and they are created in such a way. And then we have certain functions to manage those. So we have slice management function, then we have the orchestrator for those. So this is all sitting in the SMO layer. This is, let's say, related very closely to the non-real-time rig. And this is where, for example, the O1 interface is used to reconfigure what is happening down in the actual network. So speaking of the roles of the nodes in that particular context, so in the reference slicing architecture. So slice management functions are already mentioned. The 3GPP defined slice management function and sub-slice management function with extension to know that there are the ORAN elements. Then there is non-real-time rig that takes place, that has a role in the slicing part, gathering those data, applying ML AI-based approaches to interwork and to create those slices and to operate, how they operate, what are the resources needed. Should be aware of run slices and the SLA so that it could provide the policies towards the near real-time rig, and might take enrichment information, so some additional information, for example, that within a slice there are 300 users and then 2 of them are very important. They are VIPs, they need some kind of different treatment. Of course, only if there is a resource shortage that need to be applied for those 2 users. That's an enrichment information that's not taken from the run management, it's taken from another applications. Then the near real-time rig basically is responsible, it's the main entity here to control in the near real-time rig, so the operational part, where a slice is operational, optimize of the slice, optimize the resources, executing the XApps related to slicing, and then communicate with the central unit and distributed unit. It might utilize AI ML based models and other control schemes to be guided via A1 from the non-real-time rig. And we are going to see examples of those and what are the particular policies. Then CU, CP, CU, UP, there should be slice aware and execute slice specific resource allocation. They are configured through O1 when there is a slice specific requirements, and they need to be dynamically updated when there is something happening, or so that we can assure that the slice isolation. And the ODU is sort of a mixing everything together because it's related to the MAC layer, it's related to the physical layer. So there are the actual physical resources connected to it, like physical resource blocks. And then based on O1 configuration, we can allocate more or less resources to the slice. And we'll see that in a second in our examples, where MAC layer need to allocate those resources. So again, going from up, there is an awareness of slice, there is awareness of what are the policies of additional information that is provided down to the near real-time rig that is operating those and takes certain actions related to fulfill the SLA. And then OCU, CP, and the UP, they could be, the OCU, UP can be separated for each of the slice. That's a user plane processing. Control plane needs to be aware of those slices and the interactions between them. And ODU is taking the decisions of resource allocations could be reallocated via O1. The number or a portion of bandwidth allocated to it is very important here. Regarding the interfaces, this pretty much already mentioned, but to repeat that, to configure slice-specific parameters in the oran node, get some information models to provide the configuration of the slice, and gather slice-specific performance metrics. So per slice information from the OCU, ODU, ORU going up to the slice management function. A1, policy management, ML model management, and enrichment information providing down to the near real-time rig and getting the feedback of what's happening down in the network from the near real-time rig. And this is where we getting information that, for example, one slice, there is a resource shortage, we need to do something about it. And then there is a machine learning model that is providing, again, down to the near real-time rig how it should be operated. And O2, lifecycle management of virtual RAN network functions. So this is actually a specific interface that allows to create those slices in the OCloud. So create another instance of that function, or that function triggers instantiation of, for example, near real-time rig for a separate slice or CUCP and things like that, and can execute modification of the subnets and basically control how those are created. So it creates those slices. Then O1 and non-real-time rig manage them from the lifecycle perspective and overall management. Near real-time rig operates, makes the operation and decides on specific aspects. So this is how those two are created together. We have slice template, and then we have the big animal, the oran thing that is able to manage those, create those, and operate those. And then E2 to support primitives to control the particular entities down in the network, use specific XApps, and control the actions down in the network. So that's basically the description of how the network slice is taking part in the oran area. And then we're going to get some examples of how it's modeled, what are the different, let's say, variations of the representation of those things. So, for example, EMBB network slice model by ONAP. On top, we have service, EMBB service. Then we have a network slice that is, let's say, this is sort of a nested architecture, nested representation of a slice. We have a service, then we have a network slice that is supporting that service. And here we are defining certain properties. For example, the area, TA, is tracking area. So that's an area or a set of base station that is supporting that slice. This is all. Then we have, for example, a latency defined for 30 milliseconds, that there is a full mobility, and then there is a resource sharing, allowing for sharing between different network slices. So this is sort of a recipe or a requirement that should be used for this network slice. And then we have a network subnet slices or slice subnets. And this is sort of another, let's say, a nest in the hierarchy where we are, let's say, collecting different aspects. There is an NG-RAN network subnet, network slice subnet. There is a transport network slice subnet, and there is 5G core network slice subnet, right? So we have a collection of subnets that are under a control and under management of the different entities, but then they collectively create an EMBB network slice that need to have those properties. And going one step further, what we need to define is what are the different entities, and getting to our ORAN thing here. In the RAN area, we have CUCP, we have CUUP, we have RIC, we have ODU, and we have virtual links. The blue ones are dedicated to a slice, so we might create a virtual links dedicated for that particular slice, and then user plane handling, for example, robust header compression, ciphering aspects, or traffic steering, so which function or which cells are supported, that we could use, I don't know, multi-connectivity or things like that, and that's specific and dedicated to that slice. Whereas there are other ones, the green ones, they are related to, or they are shared between different slices. So for example, CUCP, the radio resource control protocol, for example, if we have a UE that is connected to that slice, so MBB slice, and another slice, then there need to be, of course, a single protocol there. So that's, in that way, it's shared. RIC is also shared, meaning that it needs to take the different slices collectively and then sort of compose and create the resource allocation such that it fulfills all of those. So it needs to be aware, it needs to be shared between different slices. Then we have a transport network that is dedicated to that slice. And then again, in the core network, we have control plane part that is shared, and then user plane part that is dedicated. This is where we can see the relation to the one we discussed in the very beginning of the session. This is where there are shared and common resources, or shared and dedicated resources, or shared and dedicated functionality related to a slice. Another way of representing pretty much the same thing in the RAN area, so that's again the EMBB service. This is where you put the information, how they are connected. Those are the different, let's say, network functions, CUUP, CUCP, and things like that. And this is also where you can see that there is a single RIC, there is a single control plane entity, and there are one or multiple user plane entities. So there is one-to-many relation. And then you can see different interfaces they are connected to. And there is also the internal ORAN interfaces also between those. So this is how you basically draw a subnet slice for the RAN area, and where you mark which functions are common and which are dedicated. Again, another example, another presentation with E2E slicing. So for example, we have one service provider, or service provider one, with the IIoT service here, and then we have the 5G core network with user plane functions. Again, it's a dedicated one, and then common AMF, and then we have the RAN part. So this is OCU CP, OCU UP, ODU, and then ORUs. And if we map on those the slicing concept, that this is the whole thing as a network slice. It also could be representing a network slice subnet, but then we have another even more granular, where there is a core network slice subnet, and then there is a RAN network slice subnet. Again, so this is very flexible, and because of that, this is also very dynamic, and how you map one to another one is a very complicated thing. This is why we need automation to make sure it's operating correctly. So those are sort of a representation of the 5G architecture with the oran in the RAN domain connected to slicing to realize certain network slice subnet. And I think the final one that is taken from the slicing architecture to actually show a concrete example mapping of the slices towards this architecture. So assume you have this, let's say, deployment. We have a regional data cloud on which we put the near real-time rig. Then we have the edge cloud with, again, virtual functions, and then cell site with the physical network functions. This is the ORU. Then we have ODU, and then we have different OCU UPs for different slices. And how we map slices to that, we have network slice subnet 1 with NSSI, so serving network slice subnet identifier 1. So that's basically a slice 1, let's say, for simplicity. That is sharing the near real-time rig. It's sharing the OCU CP. That's a single control plane element. It's sharing ODU, it's sharing the ORU, but it has a dedicated OCU UP. And the same, we create another network slice subnet or another slice, in which, for example, if we take a look on the architectural part, so this is where on the O cloud there is a definition and instantiation of another OCU UP. And then this is added to the repository. This is where the near real-time rig then manages this and things like that. So there is a need for creating another E2 connection to this. There is a need to informing OCU CP that there is another entity being popped up, because again, remember, this is all virtual. It could be instantiated and deleted. So both slices are controlled using a single CP instance and has a dedicated user plane instance. And then finally, some examples, getting back to what we had at the very beginning. This is where, for example, we could define the different timing relations. The OWD is basically one-way delay, sort of an example defined by FreeGPP or ITU. Where, for example, for the V2X or ultra reliable low latency slice, we need everything being close together. This is where we define that it should be very small. We put all the entities with the UPF and OCU UP close to the cell site at the edge cloud. Then we have another one for the MBB slice, where we could have allow more latency budget for the MBB slice, so we put it here, and then for MMTC we can put more functionality and the user plane also at the core cloud. So this is sort of a where all those relate, how they could be mapped to the particular deployment, that there is a benefit for having them as a virtual functions. They could be instantiated at the edge cloud. This is where the whole thing from the management and SMO takes place and could give you a benefit. And with that, I'm closing that part where we are speaking about, let's say, examples and details of those aspects. And then there are two more things. There are two use cases I want to take into account to actually show how there are how those functionality interrelate. what are the different policies, and what happens if there is a need for resource rescaling. So we'll start with the run slice SLA assurance. This is functionality, or this use case. Basically, what it needs to do is to dynamically allocate the resources to realize SLA. So the challenge is that the run need to fulfill requirements for each slice, like throughput, latency, reliability. That is resulting for the network capabilities that could be customized depending on the use case. For example, for one, it's high data rate important. For another one, it's service availability. For another one, low latency. And the aim is to assure that the SLA can be dynamically controlled using the slice configuration based on the performance information, and clarify necessary mechanisms and parameters. And then again, prevent violations of one SLA from one slice to another one. Now, there is a huge amount of different data that could be used for that purpose. This is why we need the overall view on the non-real-time rig, where we gather all those and apply machine learning capabilities so that we learn what happens and then act when it's needed. Again, not going through all of them, you'll get those slides so you can read them. But basically, we have the CQI-based data, we have layer 2 measurements, we have layer 3 measurements, like number of RC connections. We have the PRB usage per slice, per cell, per user, and things like that. Or one configuration data, SLA information like the service profile, what's the slice profile, what are the important aspects, and then some enrichment information. And this is what was asked. For example, location information. This is where we could get that from, I don't know, GPS or from the network when it's using the location part. So we gather all those statistics, like the radio statistics, like the performance statistics, like the configuration statistics, like the configuration of the slice, the requirements of the slice, and enrichment information like UV location. Based on that, we are sort of creating a policy through which the near real-time rig then could steer the traffic, could reallocate resources, apply machine learning model to basically dynamically change the resource allocation. So non-real-time rig retrieves this information, performs long-term monitoring, trains ML models, support deployment, and then sends those policies down over A1. The near real-time rig monitors the slice-specific performance measurements, supports deployment of the models, receive the SLA assurance XAPs from SMO, and support interpretation and perform optimized actions through E2 reports. And then E2 nodes, so OCU CP, OCU UP, ODU, depending on the part of the functionality the near real-time rig is controlling, is supporting slice assurance action, slice performance measurements through O1, and support slice performance reports through E2. So it's basically need to report that and performs no actions. So example, from E2 node, there is E2 report with the stats going up to near real-time rig. In the same time, the E2 node over O1 is sending sort of a static or default non-real-time configuration and counters KPIs from those nodes. And then non-real-time rig takes monitoring of the slice subnets, retrieval of requirements, and performs reconfiguration. And going down, so it gets all the measurements or the reports, up, performs computations and analysis, and then sends the policies for the SLA assurance down to the near real-time rig. And then near real-time rig performs monitoring of what's happening in the network and gets the policies down to perform certain actions, and then sends those down to the E2 nodes like slice assurance action and resource allocation prioritization. So for example, in that case, when there is a resource shortage, there is too many users for too little resources, what it could do, prioritize one user versus another one, allocate more physical resource blocks to one user versus another one. An example scenario, assume we have a live broadcasting slice, number one, with SLA that has defined the uplink downlink throughput of 30 megabits per second, and that the coverage of that particular slice, to be assured, is those 3 cells. Then what happens in the non-real-time rig, it gets all the information, and then need to create the policy that is needs to be transmitted down to near real-time rig, so that then the near real-time rig basically controls the resources, controls handovers, controls resource allocation in the DU based on that. So the policy will include the assurance of SLA for slice ID 1 and cells 1, 2, 3. So basically the non-real-time rig knows everything, knows that this is this kind of slice, this is this kind of SLA need to be supported, this is that coverage that need to be supported, and then creates this policy. The near real-time rig, of course, enforces that policy and guides the run behavior over this one. So example policy, again, as we know, we need to assure a certain SLA for this slice for that particular quality of service parameter, and this could be example of that slice. So policy ID 1 for slice ID 1, and of course the near real-time rig needs to know what is slice ID 1, that it refers to quality of service, or that this is I don't know, video broadcasting thing. And then, so what non-real-time rig says, well, okay, near real-time rig, please, for slice ID 1, so for this kind of slice instance, and in particular for cell ID 1, 2, and 3, so multiple cells could be supported, please assure the uplink throughput per slice of 30 and downlink throughput slice of 30. So that's an actual policy statement. Per slice, total PDCP throughput target. So whenever we define what happens, this goes to the non-real-time rig, and then it knows where to put it, what are the requirements, and then create the policy that is sent down to the near real-time rig, that the near real-time rig then controls certain resources. Enforcing those and guiding the run behavior. So what could that actually mean? It means basically that it could control the scheduler, saying that, well, I need I don't know, this kind of resources for that particular slice, because this is the target I need to assure. What that mean in particular, for example, RRM policy reconfiguration via O1. Assume we have this particular example, we have SMO, we have E2 node, and then E2 node sends the required PRBs to meet throughput, collects the CQI reports, and gets the volume of the data that is happening down in the network. Then SMO calculates the value to convert to the PRB allocation, so how many PRBs roughly should be allocated to that slice to assure that all the users have those, in total, the 30 megabits or kilobits per second, and then goes down with reconfiguring that using O1 interface with resource management policy dedicated as O1 reconfiguration request to the nodes. So to assure as a long-term performance, so average throughput does not need frequent reconfiguration. The frequent reconfiguration and the short-term performance goes over E2 and A1. So in that case, assume we have a certain slice where initial portion of calculated PRBs to assure that is that number, I don't know, 50% of resources, PRBs are allocated to this slice. Whenever, based on monitoring, we learn that this is not enough, that we are getting resource shortage that goes up to the non-real-time rig, or that it's too much, then we could, when the PRB usage becomes low, then we might reallocate that to less resources. Whenever it goes up, which means basically that we are getting more and more, I don't know, or worse performance measurements, or having that filled into, I don't know, 80% of allocated resources, then the O1 over a longer term could reallocate those slices, these PRBs that could be allocated to that particular slice. So based on that measurement, we reallocate that. But I remember, this is like sort of a long-term performance using the non-real-time rig and SMO. So this is a sort of management loop with seconds or minutes or hours. Whereas the faster adaptation with, for example, saying that for this slice, well, or for this user, we need to prioritize scheduling, that's using the near real-time rig. Okay, so that's the first use case. Second one, shorter in terms of number of slides. It's called NSSI resource allocation optimization. So that's the final point for today. In that case, we want to do a time and location-based reallocation of network resources to different slices, depending on the need. So the challenge is that the 5G network shall allocate resources dynamically among multiple network nodes to support various services realized as network slice instances. They could be, again, optimized according to service requirements, and then what is important here is that they are based on specific time or location or UE distribution. So this is a sort of more dynamic than the previous one, where we reallocate resources on the longer term. The aim and objective is that train AI ML model based on huge volume of data over days, weeks, and months to realize that there is, so I don't know, some day or some hours in a day or a particular location where there is peaks in the resources, and to predict the traffic demand in different times and locations and reallocate resources ahead of expected network issues. So in general, we do it, I don't know, as a default, and then whenever we learn that there is a need, let's say a default or a particular number of resources, whenever there is a peak, we need to do reconfiguration, and that reconfiguration can be based on long-term measurements and observation, and then immediately we can know what to do and if this peak happens. So that we don't waste the resources, because if we would allocate more resources, then we, of course, 90% of time or 99% of time will not use them. If it's predicted that it will happen only 1% or 10% of the time, then we only switch it on and allocate more resources if it happens. So again, the counters that we are using here, downlink, uplink, PRBs for data traffic, average throughput in a Gnode B, number of PDU sessions. This is sort of the data that we are using. And then we have O1 or O2 for radio resource orchestration to scale in and scale out resources, and then AI ML training at the non-real-time rig so that we can act whenever this happens. Again, what are the responsibilities here? Non-real-time rig collects those measurements, train the AI ML model, nothing new, determine and what it needs to do, that's the most important part, determine what are the specific time and locations whenever we predict that there will be a resource shortage. And then perform actions, create a policy update to the near real-time rig. And E2 node support PM collection and reconfiguration related to those resource allocation. So what happens here? We have those entities, again, the architecture. In the non-real-time rig, we have the functionality. And then, so what happens is monitoring from the E2 nodes, collecting over O1, including downlink, uplink data, average throughput, number of sessions, setup numbers, and then the NSSI resource allocation optimization performs analysis and detection to train the AI model what's happening over day and over area to determine if there is a need to reconfigure the resources. And then from one side, it sends it to the management and orchestration of the O-Cloud. So O2 interface is also employed here to reallocate the cloud resources. And on the other end, as over O1 interface, allocate NSSI resources, reconfigure the attributes over to the actual base station. So for one side, resources in terms of the processing, and then cloud resources on the other end, how to reconfigure the actual operation within the RAN. And then the final point, so how are we doing that? The goal, again, remember, it's automatically optimize NSSI resources for the models that were trained by analysis of the performance measurements collected from E2 nodes. So basically, a long-term trend observation and adaptation. So here we have the processing flow. On the left-hand side, we have the SMO, non-real-time rig. Then we have E2 nodes, O cloud management optimization, and O cloud itself. Here, remember, we don't have the near real-time rig. It's only reconfiguring the resources using O1 and O2 interface. So what's happening? Whenever the model is being trained, it gets the measurements from E2 nodes, and then it performs analysis based on those measurements, training, taking the historical management to predict what will happen in the future, determine the action based on what was done before, like what is the specific time, what's the location where it happens, what's the specific slice ID, attributes, and what needs to be done, either scaling in or scaling out. Determine the action based on this, and then execute this action via O1 and O2. So basically, reconfigure the slice in the E2 nodes, and then request the O cloud update to do it via SMO, so that it requests, for example, scale in or scale out of compute power or memory or storage. So this is basically a long-term prediction of what will happen in the future. So for example, in the Sunday night, there is a game there, or football match. So then we will for sure need these resources to do it. And on the other part of the week, there is pretty much nothing happening around the stadium, so we can decrease and scale out, scale out the resources down to some smaller number to assure just the regular traffic. Again, so that would be it. And then summarizing, network slicing is a concept. We start about speaking about network slicing, where there is a single physical infrastructure. In our case, that's the O cloud plus physical network functions, used to provide multiple logical networks to fulfill different requirements for various services. And that is including RAN, NG-RAN, and oran, transport network, core network. Network slicing is being discussed within multiple SDOs, so that's not only 3GPP thing, but also ORAN Alliance, but also ONAP, but also GSMA, but also ETSI with the virtualization of things. That's where the orchestration takes place. That's where the management is important. Then the ORAN touches slicing in the context of RAN, of course, because that's the ORAN, where the near real-time rig, non-real-time rig are responsible for resource isolation and optimization and scaling, depending on the needs, depending on the actual demand from the traffic, and use slice-dependent or slice-related XApps, RApps, and the ML models. In the ORAN architecture, again, as one of those examples, shown that the UP can be dedicated per slice to fulfill certain requirements and have certain actions like traffic steering for one, no traffic steering for another slice, one type of traffic that could be with multi connectivity, another one with only single base station connectivity, and things like that. Security different for different slices. While the OCU-CP, so RRC connectivity, and near real-time rig are shared to handle cross-slice operation optimization. So this is where multiple slices need to be, those entities need to be aware of them to play with the resources. Then one of the use cases we discussed is used to dynamically control slice configuration based on performance measurement to prevent SLA violations and assure SLA for a slice. And then another one, the NSSI resource allocation optimization, is sort of more for the platform to scale in and scale out based on the predicted traffic, depending on a specific location or specific time where the resource allocation happens. So with that, I'd like to conclude that session.